Hello everybody. We're going to do another set of notes today. This is on going from a velocity time graph back to a position versus time graph. And there's two methods that we'll be using. So we'll start off with a little bit of notes. And there'll be examples mixed in with the notes. So creating a position versus time graph from a given velocity time graph. Well, the main idea is that the velocity time graph tells us what the slopes are from the position time graph. This is the first method. It doesn't tell us anything about the actual position. It just tells us what the slopes are. So you could choose any starting position and then move from there, putting slopes in as you go. So if you have a problem that gives you a velocity time graph, first step is to see if the problem tells you anywhere, if it's stated in the wording above the graph or somewhere nearby, where the object is supposed to start. There might be a motion diagram, and the first dot might be drawn in, telling you where the motion is to start. But the velocity graph can't. In its very nature, it doesn't tell us positions. It just tells us velocities. We can figure out slopes from those. Or if there's a second method where you can actually use the area of the graph and figure out changes of position. But either way, it alone doesn't tell you where you are. So if you can get it some way from the wording or something, great. If you can't, then you get just to make up whatever you want for a starting position. You might choose the origin, but with a little bit of experience, you'll kind of scan over the velocity graph and see whether you've got mostly positive velocities or mostly negative velocities. If you have mostly positive velocities, you'll probably want to start low on your position graph because you're going to be sloping upwards a lot. Or if you have mostly negative velocities, you might want to start at a high position because you're going to be sloping downwards a lot. Determine the sections of the graph. This is number 2 in our practice. Determine the positions of the velocity graph where you've got the same velocity for that period of time. So if you've got a constant velocity for the entire velocity time graph, then you can just do one move. It's one constant velocity for the entire move. But as we go on, we're going to get velocity graphs where we have different velocities for different intervals of time. So make sure you understand which intervals there are and determine the velocities for those different intervals. And then finally, pick whatever starting position you were given or make one up that is reasonable, and then start drawing slopes from that starting position. So you're kind of shooting out into the graph, drawing a straight line with the slope you know it has to have. And then you go for the given amount of time, drawing that slope until you get to the end of that interval, and then you look for the new slope. You start drawing with the new slope for the next time interval. Okay, so let's do some examples. So on the right, we're given the velocity time graph, and on the left is a blank position versus time. There isn't any notation on the problem that tells us where we're supposed to start for a beginning position, so we can just pick whatever we want. I've got a positive slope here to start with, but then about halfway through the trip, I go to a negative slope, a negative value in my velocity graph. So I'm going to choose a starting position maybe halfway up here, and then see how I go for the drawing my slopes for these different time intervals. So for the first 2 seconds, I have to have a slope of 1. So for here to here, my line has to rise with the slope of 1. it goes up 1 meter in a time of going over 1 second. So I do that once and then again, once for each of those times, those 1 second intervals. Now I've got this down here where I've got a value of -2 for my slope. So I have to go down 2 over 1. So I'll do this. And then again, a -2 slope. So I have to go down 2 over 1. So that's my position. This is one of the position time graphs that you could draw for this velocity time. Anything that is the same slopes would be as valid of an answer. You could do that. You could start here and then go up 1 over 1, up 1 over 1, down 2 over 1, down 2 over 1. And that would be just as valid. You know, I missed on my point, but, or you could have started higher, go up 1 over 1, up 1 over 1, down 2 over 1, down 2 over 1. So any of those are okay. They are a valid position time graph for this velocity graph. All right, for the next one, I'm going to have a slope of 2 and then a slope of 1/2. So I'm going to want to start low. These are all positive slopes, so I'm going to be climbing all the time. So I'm going to pick the origin. So for the first 1 second interval, I have to have a slope of 2. So I'll go up 2 over 1. Then for the next 3 time second intervals, 1 second intervals, I have a slope of 1/2. So I have to go up 1/2 over 1. Up 1/2 over 1. Up 1/2 over 1. So it looks something like that. And then for the last one, it's kind of broken up into pieces here. We've got a -1 slope, then a +2 slope, a -2 slope, and then a 0 slope. So I think overall we're going to have a little bit of a downward trend. We've got more negative than positive, so we might want to start up a little higher. Let's start at 3. So for the first 2 seconds, I'm going to go -1 slope. So down 1 over 1, down 1 over 1. Now for the next second interval, from 2 to 3 seconds, I have to have a +2 slope. So it's up 2 over 1. Then from 3 to 4 seconds, I have to have a -2 slope. So it's down 2 over 1. And then finally, no slope. So I just stay flat. Okay. Now there is another way of doing this, and that's using this concept of the area of a plot, of a velocity time plot, the area between the plot and the x-axis. Some people will say that it's the area under the graph, but it's actually better to say, in my opinion, I suppose I should say, in my opinion, it's better to say between the plot and the time axis. Because if you're plotting underneath the time axis, you would actually find the area from the plot going up to the x-axis. And that would count as a negative area. So why an area? Well, if I was to take the motion equation that we have for constant velocity motion and move this xi over to the other side by doing a minus, So it becomes position minus initial position. We can remove those two x's and replace it with just a delta x. Delta means final minus initial, so position minus initial position would be a delta position. And then all that's left over here is velocity times time, which I've replaced the t with a delta t so that it's you can think of it as a width from a beginning time to an ending time. As opposed to in this one, it's sort of assumed that you're always dealing with the zero start, and t then would indicate your ending time. This is a more general form with the delta t. So what would I get if I took the velocity, and that's the height of this box, times the time difference from beginning to end, and that's the width of this box. Well, the units for velocity are meters per second. The units for time are seconds. So if you multiply meters per second times seconds, which is what we have here, meters per second times seconds, you get displacement. You get how far the object travels. So this is measured in meters. So this here, what we would think of as an area on this graph actually represents a displacement, a change in position. So it only has units of meters. It doesn't have meters squared. That would only occur if the two axes had both units of meters. So meters times meters would be meters squared. In this case, meters per second times seconds gives you meters as the answer. So let's use this and do some example problems. So I'm going to be shading in areas and calculating how much they represent. So for the first example, I've got the plot at -2 for 2 seconds. So the area between the plot and the time axis is this. The area of this would be a -2 measured in meters per second times a height, oh, I'm sorry, that was my height, -2 meters per second times my width of 2 seconds is -4 where the seconds cancel and I get just meters. So this is a displacement of -4 measured in meters. Now the next area is above the x-axis, so this is going to be a positive displacement. It has a height of +1, so height of 1 meter per second, and a width of 2 seconds. The seconds cancel, and I get just 2 meters. So this box, or rectangle I should say, represents a displacement of +2 meters. So coming over to my position graph, again, the velocity graph doesn't say anything about where you start. So if there's nothing here to tell us where to start, we get to pick. So I've got some negative displacement and a bit of positive, but it's mostly negative. So I'm probably going to want to start up high. So I'll start at 3. Now in the course of 2 seconds, I have to go down 4 meters. So in the course of 2 seconds, I have to go down 4 meters, which would put me underneath the position axis, which is fine. Now I'll connect the dots. So I'm down underneath at a position of -1 meter right now. Then the next part of the trip, I gain 2 meters over the course of the next 2 seconds. So from 2 to 4 seconds, I have to go up 2 meters. So I'd be here at the end of that time interval. So I'll connect those dots. So that would be a valid graph, a position time graph of this velocity graph, of the motion described by that velocity graph. Now, are there other possible correct answers? Yeah, there's an infinite number of them. So you could have started at 4. And in that case, the lines would have looked like this and this. They'd be parallel lines to the original ones. They would have the correct slopes for the right time periods. And that would also be an answer. So there's actually an infinite number of possible correct answers going backwards from velocity to position. All right, let's do the next one. So we have 2 different motions here. We have this motion traveling for 3 seconds at 0.5 meters per second. And then we have this motion where we travel at 2 meters per second for 1 second. Now, figuring out these areas, this has a height of 0.5 and a width of 3. So 0.5 times 3 gives us a displacement of positive 1.5 measured in meters. Now for this one, we have a height of 2 and a width of 1. So 2 meters per second times 1 second gives us a displacement of 2 meters. Notice the similarity with the top up here. The difference with this one, though, is that we go 2 meters in 1 second, whereas on the top one, we went 2 meters, but it took us 2 seconds to do it. So now on the position graph, I'm going to be going up the whole time, and I'm going to be gaining in position the whole time. So we should probably start towards the bottom. I'm going to be gaining a total of 3.5. So I'm going to start here, and I would expect that by the time I'm done moving, I would be up to. All right, so I'll start at 0. For the first 3 seconds, I go up to 1.5. So over 3 seconds, I go up to 1.5. And I'll connect those dots together. So just to be clear, in 3 seconds of time, I have a positive displacement of plus 1.5 meters. From this part of the velocity graph. Now for the next part, I have to go up 2 meters from where I currently am in 1 second worth of time. So starting here, going up 2 meters gets me to here. So just to be clear, in a time second, I have to have a displacement upwards of plus 2 meters. All right, the last one here. There's a lot of different areas. So for this first part, the area is 0. This has no displacement. The area between the plot and the x-axis has 0 height. So it's 0 meters per second times 1 second, which is just 0. So this has no displacement. The next one would be this area. Has a height of -2 and a width of 1. So this has a displacement of -2 meters. For the next section, has a height of 2 and a width of 1. So that's a displacement of +2 meters. And then for the last bit, it has a height of -1 and a width of 2. So this has a displacement of -2 meters. Okay, so going over to the position graph, these two areas are pretty much going to cancel out. So overall, it's only going to be this change in position at the end. So from beginning to end, I would end as -2 down from where I started. In my first move, I'm going to have to go down 2, and I want -2 from where I started. So I guess we could start anywhere at 2 or above. I think I'll start at 2. So my first displacement is 0. So I go over 1 second and not up or down. I just stay there. So that's my first displacement of 0. Now for the next move, I'm going to go down 2 meters in a time of 1 second. So in a time of 1 second, I go down 2 meters. And then for the next move, in a time of 1 second, I have to go up 2 meters from where I currently am. So I'll go over 1 second, up 2 meters. And then finally, for the last bit, I'm going to go down 2 meters in a time of 2 seconds. So in a time of 2 seconds, I go down 2 meters. So my first displacement that actually mattered was my -2, which is this displacement, down 2 meters. For my next displacement, from here, I went up 2 meters. So that's a +2 displacement. And then for my last one, I went down 2 meters, but it took me 2 seconds to do it. So overall, these two cancel, and I just get an overall net down 2 meters. All right, let's see. Done focusing yet? Okay. So I think we're just about done here. Just some wrapping up. So with position time and velocity time graphs, velocity tells you the rate change in position. So it's the delta t, well, delta x over delta t. The change in position over time is velocity. So if you're given a velocity time graph or a position time graph, you can go to the other one. If you have a velocity time graph, you can either use slopes or areas. This one is showing you areas. So the area of a velocity time graph tells you the change in position, and that will give you a possible position time graph. If you're given a position time graph, you'll take slopes. The slopes of a position time graph tells you the value of your velocity. So if I have this graph and I find the slope of it, this slope is 1.5. It goes up 6 while going over 4. So that gives me the value of my velocity graph, 1.5 meters per second for the 4 seconds that this position graph shows for motion. All right, here's some examples, some check-in questions. I'm going to ask you to do these. All right, so with the first graph, a velocity graph, what is the total displacement for this motion? All right, so it's height times width, 30 meters per second, times 6 seconds, which is 180 meters. For this next one, this is not something we'll run into in this unit because this would be a changing velocity, but the concept still applies. So if you find the area, then that would tell you how much you've changed your position. This motion is actually slowing down over time, eventually coming to a stop at 4 seconds. But to find this area, you'd have to do a triangle. So it's height times width divided by 2. So how much displacement is the second one? All right, so the height is 40 meters per second, width of 4 seconds. 40 times 4 is 160, divided by 2 because it's a triangle, and you get 80 meters of displacement. All right, in the last one, this is a trapezoid. So you could do the trapezoid equation. It's 1/2 of it's the average of the two heights times the width. So it's 1/2 of one height plus the other height, and then you multiply by width. Or you could do 2 triangles, and you'd take the big triangle and subtract off the small triangle. And I guess there is a third way. You could take this rectangle and add on to it the triangle that sits on top. So what's the area of that graph, and therefore what's the displacement for that motion? All right, so the method shown is taking the trapezoid equation. So we take the width of 3 seconds and then the average of the two heights. So it's 20 and 50, which would be 70. The average is 35. So it works out to be 3 times 35, which is 105 meters of displacement. All right, types of motion. We have an object just sitting still. The position time graph would be a line of no slope. It would tell us where the object was, and we would know that it's not moving because it's just a line of 0 slope. The velocity time graph for anything that looks like this would just be 0. Now the next type of motion, and this is part of this unit, is if we do have a constant velocity other than 0. In that case, you'd have a sloped line. It would still be a line, it would just have a slope to it. And the equation for this line is position equals velocity times time plus initial position, which is y equals mx plus b. The velocity time graph would look similar to if you were sitting still, except it's a flat line at the value of the slope. I guess this first one would be 2. But if this has a slope of 1, then the velocity graph would just be flat at 1. Now the very last graph is for the next unit where we're doing accelerations. So the only time you're going to see a curve in a position time graph is if the object is speeding up or slowing down. So you won't see curves this unit, but you will next unit. Now if you get a curved position time graph, then you're going to get a sloped, non-zero slope velocity time graph. Because in this case, the slope starts out at 0 at the very beginning, then it gets steeper and steeper and steeper. And on our velocity time graph, the value starts out at 0, and the value gets bigger and bigger and bigger. So way up here, we might have a value of, 4 or 5. That means at the end of our position time graph, the slope would be 4 or 5, which is a steep slope. All right, so for this unit, we're dealing with these first 2 situations. And for the acceleration coming up, we're going to get these types of situations with curved graphs. All right, thank you for paying attention, and I'll see you in class. Bye.